Well, good morning. This is the first lesson in recursion and exponential functions. Let's talk about it a little bit with the bell ringer. Bell ringer has nothing to do with exponential functions, but you'll get the idea. How can we tell the difference between a linear and exponential function simply by looking at the data in a table? Okay, well, I don't have an answer for this one on the thing, but I can pretty much sum it up like this. A linear function, if we were to graph it, we could see easily. And an exponential function, if we were to graph it, we can see easily. But you can tell a linear function very easy in a table if you notice that the differences between the horizontal and the vertical are equal. In other words, if you're moving horizontally the same distance every single time, that you move the same distance vertically, you're moving in a line, okay? Because rise over run in a linear function is constant. In an exponential function, that's not true. You do not have a constant rise over run. You don't have a constant rate. The rate changes, like acceleration in your car. You're not moving at the same rate between 2 points. You're actually accelerating from one point until you get to a certain speed. Then you'll go at the same rate, and then you'll decelerate when you go to stop. Those things are all explained by exponential functions. An exponential function, you'll see that the change in the horizontal is likely having common differences, but the change in the vertical will not have a common difference. You'll see that they have more a common ratio. The change multiplication is the same. You'll multiply the last value to find the next value by some particular number, and the next value after that will be multiplied by that new value to find that next value. And that's the biggest difference you can tell in a table between a linear and exponential. All right, so good things. Let's see, good things. Tomorrow, I will not be here, or actually today for y'all. I'm videotaping this the day before. You guys don't have me. You're going to have a sub. So you need to watch this, pay attention, and take the assignment. When we get back on Monday, we'll actually be doing a laboratory. We're going to look at how a tennis ball bounces and record our findings. It's a pretty cool little lab. I've done it for 5 years. It's a lot of fun. So anyway, let's move on. Tennis balls are sealed in a pressurized container to maintain the rebound percentage of balls. A tennis ball has a rebound percentage of 55% when it is taken out of the pressurized can. Suppose a tennis ball is dropped from a height of 2 meters onto a tennis court, and use the rebound rate given to predict the height of the ball's first 7 bounces. Okay, so if the first bounce will have a height that is 55% of the height it is dropped from, all we have to do is multiply the decimal equivalent of 55% by the height it's dropped from. We're given that information. It's dropped from 2 meters. So we're going to take that 2 meters and multiply it by 0.55. That nets us a 1.1 meter. So the first bounce, it rebounds up a 1.1 meter. So we can see that that rebound percentage stands for what percentage of the height will it bounce back up. And if you look at the word rebound, the definition does mean that. It means bounce back. All right, so how about the second bounce? We can't just multiply 2 by it. We're going to multiply 2 times 0.55 times 0.55. Or the answer we got from the last one, we'll multiply by 0.55. So it's actually 1.1 times 0.55, and that nets us 0.605. And we'll keep doing this. The third bounce is 0.333, or 1/3 of a meter. The fourth bounce nets us 0.183. Fifth, 0.101. Sixth, 0.055. And seventh, 0.030. Okay, so still getting bounces. But as you can see, it's pretty simple using a chart to determine the height of each successive bounce. What do you think we're heading towards, and what kind of function do you think this models? Let's write a recursive rule, though. So a recursive rule we're going to have to remember, we talked about this the last couple lessons. We're going to start with an initial value, and then we have a common ratio that we're going to multiply it by, and it's going to be an exponential function. But since we're doing recursion, we don't do that. All we do is we make an equation based on the previous value to find the next value. So the first value we know is 2 meters. Okay, because it's given. Initial drop height given, 2 meters. So that means bounce 0 or h0, height 0, or height subscript 0 would be 2 meters. And the next one, or hn plus 1, subscript n plus 1, would equal h subscript n. Now, notice how I did that. I said hn plus 1. What that means is, or n minus 1. That's the value before in the successum. The height, m, that's what it says here, but I'm using h in the lesson. If we're describing the value of the height in each successive bounce, we need to determine which bounce it is, and that's what the subscript is. It tells us which bounce it is. So at bounce 0, h subscript 0 is 2 meters. At bounce 1, h subscript 1 is 1.1. Well, what do? Let's look at the process. 2 times 0.55. And guess what? We raise that to the first power. The next one we raise to the second, third. So that's pretty easy to write the explicit function. But the recursive, what are we doing to the last value? We multiply. If hn is this, and we just substitute 1 in there, h0 is the value we multiply by 0.55. So we're going to take the subscript and we'll determine what the previous value is by taking that value and subtracting 1. So 1 minus 1 is 0. So h subscript n equals h subscript n minus 1 times 0.55. Or, since we're starting this way, we could actually say h subscript n plus 1 equals h subscript n, which means this time all we're doing is we're taking this value and we're adding 1 to it to find the next value. The subscript can be done and manipulated any way you want as long as it makes sense. So both are actually the same thing. All right, so let's take a look at what the answer is. And sure enough, h subscript n plus 1, that's 1, equals h subscript n, that's 0. So if n is 0, 0 plus 1 is 1. So h subscript 1 equals h subscript 0 times 0.55. Let's check our answer. So if h subscript n plus 1 is 1, h subscript n is 2, because it's 0, bounce, times 0.55, and 2 times 0.55 is 1.1. So we have to describe it this way, where n equals 0, 1, 2, 3, and so on, and h subscript 0 is given at 2 meters. So, describe in words how the height of each bounce is calculated from the height of the previous bounce. This is really simple. And this is a good way to look at the way a tennis ball bounces. Notice that if we were to graph this, what kind of graph do you think that models? You see how it gradually lowers? The height of each bounce is 0.55 times the height of the previous bounce. That's how we describe that recursive formula. So think about it. The height of each bounce, h of subscript n plus 1, is 0.55 times the height of the previous bounce, h subscript n times 0.55. So we're going to graph the bounce and height columns in a graphing calculator. So let's go ahead and do that. I think I've already put it in here. So what we do is we take these values here, move up. There we go. I don't know if you can see that. Let's get rid of this transitions line. Okay. Well, that's not the one I'm looking for. Let me get rid of this real quick. There's my big old mug. Move this over a little bit. Now, pull my calculator out, and I'm going to go, and I've done this already to show you. You will put bounce number in column L1, 0 through 7, and the height in column L2, or H in column L2. And what I've done, and this is really cool, I'm going to point this out to you. This says 1.1, but I can actually put an equation in here. So 2 times 0.55, that should get me, if I put that in here, right here, in there, I should get 1.1, and I do. Okay, so that's what I did for all of these. And if I want to graph it, of course, we're going to hit zoom 9. So zoom 9. There it is. What did I do here? Let me turn this off real quick. I'm going to clear that. Now we'll graph it. Zoom 9. Why is it still there? Shouldn't still be there. That's all right. Zoom 9. I don't know why that's there. I think they're putting lines between it. That's okay. Doesn't matter. Let's go back to the function. Let's go back to the presentation. And sure enough, the very next slide will show the exact same thing we have on our calculator. Scatter plot of the data table is last slide shown. Describe the data well by showing the decay of the bounce as gravity takes more and more control over the ball. Now think about that. That's what's going on. The bounce, if we had no gravity, you wouldn't even see a bounce, and the bounce percentage wouldn't matter, because what would happen is it would hit the target or hit the ground and bounce back up and not come back. In order for that to work, though, you wouldn't be dropping it. You would have to throw it. There has to be some kind of force on it. In this case, the force we use is just the gravitational pull of the Earth. So it takes it down to the Earth and it bounces it back up, and gravity takes a hold again, and it takes a hold and it goes back down to the Earth and it bounces back up, and then until gravity takes over, until it takes so much control over the ball, it can no longer bounce. All right. Now, what kind of function might model the tennis ball bounce situation? Linear makes no sense, because as the ball bounces, the height gets smaller and smaller until it approaches 0. If it was linear, the bounce would be the same, or it would bounce the same difference every time. So in other words, you'd start at 2, then it would go to 1.9, then 1.8, then 1.7, then 1.6, then 1.5. That doesn't make any sense, does it? It's not going in a line. Instead of a constant difference, like a linear function does, the ratio between them is constant. So in other words, we're multiplying by the same thing. The height is multiplied by 0.55 every time. So we get a new height that we drop from, and if you think about it, that's exactly what's happening. You drop the ball from 2 meters, it bounces up 0.55, and that's when gravity takes a hold of it again. It stops going up and starts going back down again. So we're dropping it again from a different height, and this time it would be 1.1. And then it would drop and bounce up 0.55 or 55% of 1.1. And that's exactly what's going on. An exponential function has to model the data. All right. Let's look at this table of values, and we'll talk about the first differences and the successive ratios. So, first bounce, 1.1. A difference of minus 0.9. The ratio is 0.55. Next height, 0.605. Difference of 0.495. Ratio is still 0.55. Guess what? You see something about those first differences? They are nowhere near the same thing. Matter of fact, those differences have the same ratio as the height. This difference, 0.9, if you multiply by 0.55, you get 0.495. Just to prove that point, let's take the calculator and double check it. And this will be something we'll learn again. So it's minus 0.9. Let me clear this. Second quit. Minus 0.9 times 0.55 minus 4.95. Minus 0.495. I'm sorry. So yes, exactly. We have the same percentage in the first differences that we have on the actual bounce. That's not strange. That's by design. And that's exactly how it works. All this information is the same. All of these differences here have the same ratio as the differences in the bounce. Okay? So let's look at the table we generated and write a function rule for the bounce height in terms of bounce number. So in other words, we're going to write an explicit rule. This explicit rule, we're doing something every time. What are we doing every time? We're multiplying by 0.55. Well, that easily explains the recursive rule, but what about the exponential rule? What we're looking at here is 0.55. We're multiplying by 2. And then we're multiplying 2 times 0.55 times 0.55. And then we're multiplying 2 times 0.55 times 0.55 times 0.55. An exponential function obviously has an exponent somewhere. It's obviously going to be multiplied by the 0.55. So our function rule, height of the bounce, and n equals a bounce number, then 2 times 0.55 raised to the n power. The graph of the function rule passes through all the data points scatter plot. Let's look at that on our calculator. So we can actually use regression, stat, enter. We have this information in here. Let's use regression, stat, calculate, go down to exponential regression. There it is, 0 right there. Let's hit enter. I want to calculate this information. Look at that. Y equals A times B raised to the X power. A equals 2 and B is 0.55. Guess what that means? Exactly what we just said. Let's put that in here. Y equals 2 times 0.55, and we're going to raise that to the n. Now, I know it says X, but it doesn't matter. Now I'm going to zoom 9 this and see if it follows it perfectly. 9. And it sure does. Let me see if this scatter plot has something fun. Yeah, it's a line plot is what it is. That's why it's doing a line plot. I'm going to change that to a scatter plot. That's why I wasn't doing it. No. Change this, delete it. Now when I zoom 9, scatter plots works perfect. Now I'm going to put in y equals 2 times 0.55. Oops. 2.55 raised to the n power. Oops, that's not right either. Delete that. Raised to the n power. Now when I zoom 9 it, not only will I have the scatter plot, but that graph runs right through every point. So that is the exact rule we need. So just like the graph or the presentation says, we can see from our calculator that we're getting the same information. All right, let's move on. What is the height of the fifth bounce of a new tennis ball if the initial drop is 10 meters above the ground? And we're going to use a function rule to find our answer. The new rule is h equals 10 times 0.55 to the n power. Very similar to the last one, just the initial height has changed from 2 to 10. So instead of a 2 here, we just put a 10 there. So the height of the ball after the fifth bounce is h equals 10 times 0.55 raised to the fifth power, or 0.503. And let's check that on our calculator real quick. This should be real simple. 10 times 0.55 raised to the fifth power. Sure enough, 0.503. Okay, we're getting some good information here. The screen loads so slowly. All right. All right, suppose a new tennis ball is dropped from 20 feet. How many times does it bounce before it has a bounce of less than 4 inches, which is the diameter of the ball? And we'll explain our solution. So this is pretty simple. The rule, we're going to change that 10 or the 2 to 20. And from the table, we can see that the sixth bounce, n equals 6, and the height is about 0.55 feet, which is about 6 inches. By the seventh bounce, the ball bounces less than 4 inches, or the diameter of the ball. So 11 feet is the first bounce, 6.5 or 6.05, 3.3, 1.8, 1.0. We don't get down to 4 inches until it's 0.25 or less. 0.25. Is that right? 0.25 feet. Yeah, because this is in feet. 0.25. No, that's 3 inches. 4 inches is 1/3, so it has to be less than 0.33. So the 7th bounce is less than 4 inches. Because, and we'll look at this on the calculator, 0.304, we'll find out exactly how high that bounce is. 12 times 0.304, it's 3.6 inches. And yes, it's less than 4 inches. So yes, we're golden. So we got that information really good. We can see that the exponential function is easily determined using an explicit rule. And we know how to do it now with a recursive rule. So what is the total vertical distance up and down that the ball has traveled, fallen and risen after 6 bounces? Explain your answer. Total vertical distance is the sum of the heights h0 to h5, which gives how far the ball has fallen during 6 bounces, and the sum of the heights from h1 to h5, which gives how far the ball has risen. All right, so total distance fallen, 20 plus 11 plus 0.605 plus 3.3275. Notice this is the distance fallen. We do this again, risen. We add all the numbers except 20 because it fell 20 feet, then it fell 11 feet, then it fell 6.05. And if you want to do it in order, it fell 20 feet. Then it rose 11 feet, then dropped 11 feet. Rose 6.05 feet and dropped 6.05 feet. So we add these two together, and the total vertical distance that ball has traveled is 66.982 feet. The total vertical distance the ball has traveled after 6 bounces. So, now as our population uses more antibiotics for minor infections, bacteria adapt and become more resistant to the medications that are available. Methicillin-resistant Staphylococcus aureus, or MRSA, is a strain of Staphylococcus bacteria that is resistant to antibiotics. It causes skin and respiratory infections, and it can be fatal. The CDC reported that in the United States, 94,360 MRSA infections occurred in 2005, with 18,650 of these cases resulting in deaths. That's a lot of deaths. And to put this in perspective, 18,000 is about 20, 94 is about 100. That's 1/5 of the people that got it died. Now, to put this number in perspective, CDC reported 16,316 deaths related to AIDS. So MRSA is killing more people than AIDS is now. And that's back in 2005. It's 2020. That's 15 years ago. There's a really good way to keep this from spreading. Wash your hands. All right. Research lab is observing the growth of a new strain of MRSA in an agar dish. An agar dish, that picture right there, that's an agar dish, okay? The initial area occupied is bacteria is 2 square millimeters. In previous experiments with MRSA, scientists observed the bacteria to increase by 20% each week. Now we're going to fill in this table showing the increase in area of the bacteria over 8 weeks. And we're going to write a recursive rule. Okay, so first day, we increase 2 square millimeters. Okay, is that right? 2 times 0.02 plus 2. So think of what it's saying. The initial area occupied the bacteria is 2 square millimeters. Okay? We have to add the 2 millimeters that we started with. We're going to show the increase and add it to what we already have. So it's 2 times 1.2. So in other words, we have an increase of 120%. If it grows 20%, then it's growing a total. The increase is 1. The common ratio is 1.2. So after 1 week, we have 2.4. After 2 weeks, 2.88. 3 weeks, 3.456. And you can see the growth becomes a little untenable or unmanageable. After a while, it gets crazy. This is our rule. The growth in millimeters square is designed by multiplying the last value times 1.2. So we can find any value as long as we do the last value by multiplying that last value by 1.2. Now, this is not efficient if you want to know the 120th week. So we can do this as long as we don't know the first 8 or 9 weeks, something like that. We can do that easily because we're using the last week's value or area that the MRSA is taken up to find the next week's value. All right, we're going to make a scatter plot. And notice it has that slight curve. Guess what? You're right. It is an exponential function. Now, I'm going to launch you with this. MRSA can grow unmitigated or unstopped when it's not noticed. It took a toll on prisoners in the 80s. While generally not lethal, MRSA can cause major infections that can enter the bloodstream and wreak havoc on a person's immune system. Now, this is where MRSA becomes deadly. The simplest way to stem the errant spread of any infectious germ is to wash your hands. And that is so true. However, I want to point something out. You can get a MRSA infection anywhere on your body. Your body carries bacteria on its skin no matter how much you wash it. You can wash it 1,000,000 times. There will be bacteria growing on your skin. Bacteria likes dead cells. It feeds off of the dead cells your body sheds. And we have to regenerate the cells in our body. I don't know if the science to this. If you don't know the science to this, we have to regenerate our entire body, probably, except the nerves, I think, several thousand times before we die. And it's ridiculous. We have a new body about once every year, and that's true, except for our hair. We keep that. And our teeth, and our bones. So you really need to be careful and wash your body very well on a regular basis. But I would also not use antibiotics a lot, because that's what helps these bacteria become resistant. The more we use them, the more resistant they become. So there's a lesson in the Google Classroom. Be sure to take care of that right away. In the meantime, be blessed and be a blessing.